One of the most impactful pieces of engineering is the technology of movies. They've shaped every aspect of our lives. Today, of course, they are created digitally, but I celebrate here the stunning engineering that gave life to movies in the 20th century, all to trick the mind into seeing a moving image. Now, to show you, I have this 16mm projector, which was typically used in schools. Film came in many sizes, from the giant 70mm, popular in the 1960s for epics like Lawrence of Arabia, to 35mm used for most feature films, to 16mm for schools, and even 8mm used by home enthusiasts. The larger the film, the greater the resolution, of course. All worked with a mechanism similar to this projector. Here's what I'll show you.
How the film is pulled from the supply reel continuously, then intermittently pauses here to project the images, then again moves continuously here to play the sound.
To create the illusion of movement, still images, the frames of the movie, zip by so fast that our eyes see fluid motion of the screen. It isn't quite that simple. To see that, here's what's happening if you just move the film continuously past the projector's lamp. What you see is a blur. You can just make out the images.
Here's what actually happens in slow motion. A frame appears on the screen, not moving, then the screen goes blank, and then the next frame is projected on the screen. The projector must hold the image on screen for a moment, then cover up the image while the film moves to the next frame. Two mechanisms do this. First, the shuttle. The shuttle has 3 teeth which engage the sprocket holes in the film. The shuttle moves back to disengage from the film, then moves upward, then forward to engage the film, then moves downward, pulling the film with it. The film is stationary most of the time and only moves when the shuttle is moving downward. This is the intermittent motion of the film that is required to avoid blurring of the projected image. Here is slow motion footage of the shuttle moving up and down intermittently. From this angle, you can clearly see the shuttle move forward and back to engage and disengage from the film. The shuttle transports the film so that it is stationary most of the time and quickly advances to the next frame. Though it is rapid, the film movement will cause blur in the projected image. This is where the shutter comes into play. The shutter is a disc with a blade that protrudes from half the circumference. The other half is open. The shutter rotates once every frame and is synced so that the shutter blade blocks light from the lamp when the shuttle is advancing the film. This prevents film motion from being projected on the screen. Both these mechanisms, the shutter and the shuttle, are driven by a single axle. The shutter has a single degree of movement. It rotates along with the axle. The shuttle mechanism moves in 2 directions. The shuttle moves up and down, as well as forward and backward. The teeth of the shuttle are held in place by 2 shuttle arms. In between the arms is an eccentric cam. This cam rotates with the axle and moves the shuttle arms up and down. The outline of the cam has a constant width so that the distance between the top and bottom arms doesn't change. The cam also has an asymmetric shape. This asymmetry makes the shuttle hold steady at the top and bottom of its travel. To see how the shuttle moves forward and backward, let's look down from above. The shuttle arms act like a third-class lever. They pivot on one end, and at the other end there is a spring force pushing it forward, as well as an effort pushing it backwards. This backwards effort is created by a disc tilted a few degrees off the axle. When the axle turns, the disc wobbles. A pin connected to the shuttle arms is pressed into contact with the wobbling disc by the spring force. As the axle turns and the disc wobbles, the shuttle arms are periodically pressed backwards. This movement is synced with the eccentric cam to create the required motion of the shuttle. The film passes by the lamp at 24 frames per second. At that rate, the human mind will blend the still images into fluid motion. A projector with a single-bladed shutter blocks light to the screen once every frame. This means that half the time, every 24th of a second, the screen is dark. This alternating between a bright projected image and darkness is called flicker. If the flicker occurs at a fast enough rate, about 60 to 70 Hertz, the bright flashes fuse together and appear, to the human eye, to be continuously bright with no periods of darkness. This rate is called the flicker fusion threshold. Since 24 flickers per second is below the threshold, the flicker is visible. This flicker is the origin of the term flick. But modern film projectors don't have this problem. How did they fix it? The obvious way to get rid of flicker is to film at a faster frame rate. However, that would be bad engineering. You would need much more film, and film is expensive. Recall that 24 frames per second is fast enough to see fluid motion. It is only the flickers per second we need to increase. So the solution lies in the shutter. Originally, shutters had a single blade that covered the advancement of the film with an open section that showed the picture. Modern shutters have 3 blades. The first blade covers the film motion. The second 2 blades block the light even when the film is stationary. They only serve to increase the flicker rate. The 3 openings allow the image to be projected half the time. The 3-bladed shutter is a simple and inexpensive solution that works well. The frame rate stays at 24 frames per second, and the flicker rate is increased to 72 flickers per second, above the flicker fusion threshold. So the movie appears to move smoothly without distracting flicker. So if you watch a film in slow motion, you will see that a single frame is flashed on screen 3 times before the next frame is shown. Sound in movies is recorded optically on the edge of the film. After the film runs past the lamp, it runs across the sound drum. To read this optical soundtrack, light shines through a tube with a slit. This concentrates the light on a small section of the film's soundtrack. A photodiode on the other side of the film measures the amount of light passing through the film at a given time. The photodiode converts the amount of light transmitted into current, and this current drives the speakers. Wide areas of the soundtrack correlate with loud noise, and thinner areas are quieter. For the sound and image to be correctly synced, the soundtrack is offset 26 frames ahead of the picture in 16mm films. The addition of sound is what made movies run at 24 frames per second. Early movies ran at 16 frames per second, which was just adequate to create the illusion of moving images. But when sound came along, 16 frames a second was too slow. The highest frequency that could be recorded was 6,000 Hertz, just barely enough for spoken dialogue. It was kind of tinny, but too low to reproduce music. 24 frames per second allowed for sound up to 9,000 Hertz. A subtle but important part of film projectors is the film loop. The loop allows the intermittent motion needed to project and the continuous motion needed for sound to work together. This top sprocket pulls the film from the supply reel continuously. A loop of slack film starts to form. This slack allows the shuttle to quickly advance to the next frame without tearing the film. A second loop of slack film at the bottom also forms. The bottom sprocket pulls the film continuously across the sound drum, allowing the soundtrack to be read correctly. Film projectors, while artifacts of cinema past, contain brilliant engineering that helped create the flourishing world of TV and movies that we enjoy today. I'm Bill Hammack, the Engineer Guy.